In this video, I'm going to provide a solution to the scaffolding problem that we did recently, where we have a meter stick with supports at 30 centimeters and 70 centimeters. And we're going to take an object, some mass here, and we're going to move it further and further and further to the left and ask the question, how far from the edge of the meter stick can it be and still have this system be in equilibrium? And we're scaling this problem down from a scaffolding problem where maybe this is a board that's hung on the side of a building that's held up by a couple of points, and we wanted to know how far the person can move over before the thing starts to rotate. So when it starts to rotate, the equilibrium is being disturbed. So where's that equilibrium coming from in the first place? So what we could do is we could look at the forces that are acting on this system. In this current state, there are several forces that act. There's a normal force from this support here that points upwards. We'll call that N2. There's a normal force from this support that points upwards. We'll call that N1. The meter stick has a weight which points downward, and that acts at the center of mass, which would be between the 2 points of support. So mg points downward. And then that mass, wherever it is going to have a gravitational force that points downward as well. And maybe I'll call the mass of the meter stick ms, and I'll call the mass of the object mo. So these are the forces that act on this system, and apparently the mass of the object plus the mass of the meter stick are balanced by these two normal forces. And that can be true no matter how much mass I really put on top of the meter stick, because the more mass that I add, the more force there is between the contact points. So long as the meter stick doesn't break, those normal forces can always increase to keep the thing in equilibrium. So the forces are balanced, but as I move that object further and further to the left, the torques become unbalanced. And one of the conditions for equilibrium is that the net torque equals 0. And so if I disturb that condition for equilibrium by making one torque or several torques greater on one side of the axis of rotation than the other, then that can cause a problem, and it can cause the rotation of this system. What I showed you in class is that if I move that object far enough to the left, eventually we get to a place where N2, that normal force that I've drawn, goes to 0. And it goes to 0 because that part of the meter stick at this contact point here is essentially resting just above the support. The support's not actually doing anything. And so when that happens, what does the picture look like? How is it different? Well, this normal force goes away, and the object is being very close to the point where it could rotate. If I move the object a little bit too far, then it will start to rotate, and the question is, where will it rotate about? What's the axis of rotation? That axis of rotation is the other support. And so let's look at what's left in the picture. I have the weight of the meter stick, which points down on the right-hand side of the meter stick. I have the weight of the object, which points down on the left-hand side of the meter stick. Since the axis of rotation is at the location of N1, that normal force, then that force cannot cause a torque, and so it doesn't influence this net torque that I'm talking about. So although that force still exists, I'll cross it off because it doesn't generate a torque. One way to solve this problem is by working with these two forces alone. And so that's going to be the first way that I'll solve it here. It's not the way that I described when I initially presented this problem to you, but it's one way to do it, and arguably a simpler way. Sometimes the way that I like to solve a problem isn't always the best way or the simplest way. It's just the way that makes the most sense to me. So I'm going to provide one solution here, and then I'll describe the modifications that could be made in order to solve it in the way that I originally solved it. In this case, with this free body diagram, we've pretended that the meter stick is not a long object that has a length of 1 meter. We've said that the meter stick is an object that exists at one point, the 50 centimeter line of that meter stick, and it has a mass ms. So that yellow dot that I've drawn, that is where the meter stick is. Okay. The weight of that meter stick then is going to cause a torque in this system, and that torque that it generates causes the system to rotate in this way, right? Clockwise. The object on the left-hand side of the axis of rotation would cause the system to rotate in the other way. It would be a counterclockwise torque. And so what we're seeing here is a balance between those two torques. The torque due to the object equals the torque due to the meter stick, TS, or tau S. Another way to write that, if you're curious, right up here for my net torque equation, the net torque equals, if counterclockwise rotations are positive, then minus the torque due to the stick plus the torque due to the object equals 0. And that's where I get the fact that those two torques are equal. If I remember that any general torque, tau, equals RF sine theta, then what are the torques in each case? On the left-hand side, I have the weight of the object that is going to be a certain distance r away from the axis of rotation, which is this green dot that I've drawn. So I'm going to label that r, and I don't know what that is yet. But in my torque equation, I'm going to include that r. The force that is being exerted at that distance r is equal to mg, where m is the mass of the object, times g. And sine theta would be the sine of 90 degrees, which is equal to 1. Why is it 90 degrees? Because this blue line that I'm drawing is r. R is the distance from the axis of rotation to the force. And mg is that downward red arrow that I've drawn, and so those two things are perpendicular to one another. That torque due to the object is balanced by another torque, the torque due to the meter stick. And the torque from the meter stick is due to the weight of the meter stick, which is acting at the center of mass. So we are assuming that the meter stick has a uniform mass distribution, and that allows us to just say that the mass, or the weight of that meter stick, is all concentrated at one point. And what is that distance between that one point, which is the center of mass, which is the center of that meter stick? That would be the 50 centimeter line. And so if the axis of rotation is at the 30 centimeter line, then the distance between those two things would be 20 centimeters. And so for now, I could put in some other variable, maybe like R2 or RS or something like that, but I could also just plug in the fact that it's 20 centimeters. As long as I know that I plugged in 20 centimeters for that distance, then I'll know that later when I find my R value, or when I find X, that answer is also given in centimeters. Here, if you don't make the conversion, it works out okay. So for the torque, that distance that I need to include for the weight of the meter stick torque will be 20 times the force, which is ms times g, divided by, multiplied by sine theta. And once again, we have the fact that those two things are perpendicular, and so we have the sine of 90, which is 1. So in this equation, what I'd like to do is solve for r. And what I see here is that r equals 20 msg divided by m of the object times g. The acceleration due to gravity cancels, and what I'm left with is 20 times the mass of the meter stick divided by the mass of the object. If those two things are given in grams, then I could plug those in and solve for r in centimeters. And I think for the example that we were doing in class, the mass of the meter stick was on the order of about 150 grams, and the mass of the object was on the order of 200 grams. And so we could do some simple math to say that maybe one of the zeros cancels with one of the zeros. 2 divided by 20 is 1 over 10. And so 150 divided by 10 gives me about 15, right? And so hopefully 20 times 150 divided by 200 is about 15. Now r is not my answer, but I can take r now and express r in terms of x, because x is the thing that I was looking for. The question was phrased such that how far from the edge of the meter stick can the object be? And so the way that I solve for that is I say that x plus r, those two things together, go from the 0 centimeter line all the way up to the 30 centimeter line. And so those two things added together give me 30. And if I just found r, and r is equal to 15, then I know that x is equal to 30 minus 15. And so x is equal to 15 centimeters. Which means that if I start walking along this meter stick, or a wooden plank that has similar dimensions, right? If we scale everything up but keep all the restrictions of the problem the same. If I keep walking, I can go all the way out to 15 centimeters. At that point, the support at 70 centimeters would no longer be supporting it anymore. And if I move any more, then I'll start rotating about that 30 centimeter line. One thing I'd like to caution you with here is I'm about to give a slightly more tedious way of doing this problem, and one of the things that I'm going to mention in that problem is that the mass is not necessarily going to be in the middle of that left section of the meter stick. Here it is, 15 centimeters, right? That 15 centimeter line is right here, right in the middle of that left chunk of the meter stick, because it's 30 centimeters long and it's at 15 centimeters. But if you look at the math, right, I did some quick math there to get to 15. If I had a different mass of the meter stick or a different mass of the object I had on there, then I wouldn't necessarily get 15. So you need to make sure that you know that that really is a variable position, x, that depends on what the masses of the objects are relative to one another. So taking that now, I'm going to go into a slightly different way of solving the problem. Let's take a second look at this picture and try to solve it a slightly different way. In this solution to the problem, I'm going to say that the mass of the object times gravity still points down at some location there. The axis of rotation is still that left support that we had. The object is still a distance x away from the axis, or sorry, from the edge of the meter stick, and from the axis of rotation to that object, we have the same capital letter R, which represents that distance, that variable distance. But instead of having one torque due to the weight of the whole meter stick, which might be non-intuitive to some of us, it might make clear sense the way that I explained that problem the first time, but maybe this will make more sense to some of you. To say that instead, the axis of rotation is effectively dividing this meter stick into a couple of different pieces. We have the piece on the left and the piece on the right. The piece on the right is 70 centimeters long because this support is at 30 centimeters, which means that the piece on the left-hand side is 30 centimeters long. And so what I'm going to say instead is that at the center of this piece on the right, that section of the meter stick has its own little center of mass, which is, let's say, the mass of the right side times g. And on the left-hand side, the center of mass of that little section of the meter stick has its own little mass, and we could call that ml for the mass of the left side times g. The reason why I like to think of the problem this way is because now instead of just two torques balancing, we can separate the two sides of the meter stick and say on the left-hand side of the axis of rotation, right, the axis of rotation is this 30 centimeter line. On the left-hand side, I have a torque from the object, which is a counterclockwise torque, and I have a torque from the left side of the meter stick. Those two things are causing the system to rotate counterclockwise. On the right-hand side, I have a torque due to the right side of that meter stick. And so, to me, it seems like just physically that it makes a little bit more sense to handle the problem this way, although it does make the solution of the problem a little bit more difficult, because now, of course, I've got to work with 3 torques instead of 2. And how do I figure out the mass of the left side of the meter stick versus the mass of the right side of the meter stick? The way we're going to set up the problem is in principle the same way. The torque due to the object is still the distance from the axis of rotation to that object times the force, which is MO times G. Sine theta is still going to be sine of 90 degrees equal to 1 for all three of these torques. The torque from the left side of the meter stick, we've got to be kind of careful. How far is it from the axis of rotation to the center of mass of the left side of the meter stick? We know exactly what that number is. It goes from here to here. It's half the length of the left side. If the whole length is 30 centimeters, because the zero line is at the edge, then half that length will be 15. And so my torque is going to be R, which is that distance there, 15, times the force. The force is the weight of the left side of the meter stick, which I've expressed as ml times g. And maybe for a moment I'll just leave that there. And now we'll go over to the right-hand side. Those two torques on the left have to be equal to this torque on the right-hand side. The right-hand side, the distance from the axis of rotation to the center of mass of the right-hand side would be what? Well, the right-hand side is 70 centimeters, so half the length of that right-hand side would be 35 centimeters. If you care about the specific number, what is this number that this position is at? Well, it would be that 35 that I've just drawn in plus the 30 on the left. So altogether, if you were looking at the meter stick, that would be the 65 centimeter line. The torque, though, depends on the distance from the center of mass of that right piece to the axis of rotation, which is just 35. So 35 times, for now, the mass of the right side times g. Okay. Notice that g cancels, so I can cross off g because it's in every term. And what I'm left with is r times the mass of the object plus 15 ml equals 35 mr. And what I have to do now, unavoidably, is figure out how to express the mass of the left side and the mass of the right side of the meter stick. You can put a meter stick on a scale, and let's say that it reads some value, maybe ms equals 150 grams. How do I know how much of that weight is on the left and on the right? Well, if the left side is 30 centimeters and the right side is 70 centimeters, then I can express the length on the left or the length on the right as some percentage of the mass. So what I'm going to do is I'll write r times m of the object plus 15 times, instead of the mass of the whole meter stick, to get the mass of the left side, it's only 30 centimeters, and 30 centimeters is 3/10 of the whole meter stick. So what I want is 3/10, or 0.3 times the mass of the meter stick. So 0.3 times ms. And on the right-hand side, I'll have 35 times the mass of the right-hand side, which is 70 centimeters, so it's 7/10, or 0.7 times the mass of the meter stick. And so what I'm left with is r times the mass of the object plus 15 times 0.3, which is 3/10 of 15, which is 5 ms, equals 35 times 0.7, that's 7/10 of 35, which is 24.5, times ms. Ultimately, what I'm looking for is r, right? R up in my picture was this variable here, which I can ultimately then relate to x. So we need to solve this for r. And the way that we do that is we say that r times the mass of the object equals, let's subtract the 5 ms over to the other side. 24.5 ms minus 5 ms is 19.5 ms. And so we get r equals 19.5 ms divided by the mass of the object. And so if the mass of the meter stick is 150 grams and the mass of the object is 200 grams, what do we get? 19.5 times 150 divided by 200. That gives us R equals 14.625. And so if I want to find x, remember that x plus R equals 30. And so if R equals 14.625, 30 minus 14.625 is 15.375, or maybe about 15.4 centimeters. So I can move that object further and further to the left until I get to about 15.4 centimeters. So a slightly different way of solving the problem. Of course, here you might be saying, why do you go to the length of solving the problem two different ways? Well, first I'm trying to show you that there's different ways of solving the problem, and actually they're quite different here. And here it didn't matter which way you picked, but maybe there's a problem in the future where if you don't know how to do the problem in a certain way, based off of the given information, you're maybe restricted a little bit. Lastly, I'll point out that here I got 15.4 centimeters. In the previous version, I got exactly 15 centimeters. That's probably due to some rounding errors, and also sometimes when you solve a problem differently, the way that the numbers work out in the equation might be slightly different, but we get essentially the same answer of about 15 centimeters.